Hello and welcome to Accelerate Database Development and Testing with Amazon Aurora. My name is Vlad, and presenting with me today here is Steve. We're both solutions architects with AWS, focusing on databases and specifically Aurora. So why are we having this session today? What we really see is that there's no longer so much of a segmentation between the responsibilities of the different roles that are involved in applications. You have developers, you have DevOps folks, you have DBAs, you have system administrators, and they're all collectively responsible for things like the architecture of the application, including the architecture of the database, deployment and automation aspects of databases, optimizing and improving the outcomes of dev and test scenarios and pipelines, focusing on performance from the get-go, from the architecture and implementation and development side, and generally, keeping costs as lean as possible. So all of these responsibilities, they're no longer segmented, where the DBA is worried about the operational aspects, the maintenance of the databases, and developers are just trying to get their applications running. So it's more of a collaborative effort, right? And in today's world with databases such as Amazon Aurora in cloud environments, we do provide native capabilities that help you achieve this goal easier and faster and be generally a lot more agile. So when we're thinking about optimizing development and testing outcomes from a database perspective, if we're looking at kind of that entire life cycle of an application, you typically, when you deploy an application and adopt a database, you're thinking first, well, gee, what is the most effective way to architect this? How do I plan it? What features am I going to use? What is the architecture going to look like? And then from there, you transition into deployment and automation. How do I take this and deploy it? How do I make it repeatable so I can have many numbers of pre-production environments that are used for development, testing, QA, and so on and so forth. Everything being repeatable, everything looking at relevant data sets, and then finally transitioning into obviously production. When you're developing, you want to make sure that you're developing with the scale at production in mind, right? You want to make sure that your queries are optimized from the get-go. It's not an afterthought that some DBA somewhere has to worry about once you've already built the application. That no longer really happens, right? And then, of course, cost is a big consideration across the board for all of these activities. So let's look at how this impacts decisions around Aurora and how best to leverage technologies like Amazon Aurora for these type of use cases. And let's cover architecture and deployment automation first. Really quick, just for the folks that might be perhaps not as familiar with Amazon Aurora. So our Amazon Aurora is a cloud-native database. So what we've done is we've taken the traditional, mostly monolithic model of a relational database and adopted and implemented a lot of the scale-out cloud patterns in the process of reimagining it. So, Amazon Aurora has a scale-out distributed storage architecture with purpose-built storage services that are designed to handle database-type workloads and database-type interactions. And it's a service-oriented architecture leveraging AWS services. It's built on top of the same core AWS services that we use and provide to our customers as well. The compute nodes are provided through EC2. The storage is built on our own services. It integrates with identity and access management for, potentially authentication as well. It integrates with Lambda, invoking asynchronous or synchronous Lambda functions directly from your database. It integrates with S3 for imports and exports. So it has a wide field of integration with our ecosystem of AWS services. But most importantly, it's a fully managed service where we automate the administrative tasks, part of the storage layer, so you don't have to worry about things like backups, things like patching, how to set up high availability and maintain high availability. All of that and much more is provided through the service. And all of these, cloud-native capabilities really do make it easier for you to use, which makes you, in turn, a lot more agile. And it makes Amazon Aurora really, really fast as well, because we're doing more fundamentally with less resources. We're optimizing. So you'll see that, for example, Amazon Aurora can achieve 5 times the throughput of a traditional community edition of MySQL implementation that is similar in scale, right? And it can achieve 3 times more throughput than a comparable Postgres environment, open source Postgres environment. But when we're thinking in terms of development and testing, there's really 3 characteristics that, from an architectural point of view, that we like to key on, that are really important whenever you're planning in your architecture environment. One is the fact that I mentioned that the log structure is custom built and is log structured and is distributed, but really that storage volume that you have on an Aurora cluster is shared by all of the cluster nodes. All of the cluster nodes, the reader and any number of read replicas you might have, up to 15, they all see the same data structures. And from that perspective, the readers in an Aurora cluster are strictly read-only. When you're thinking in terms of a more traditional MySQL environment, for example, if you want read scaling, you achieve that using binary log replication, which means you have a different instance where you replicates your binary logs to. That instance then applies all of those logical changes to its own storage. There's an overhead for doing that, and if you have many read replicas, again, each one has its own storage, each one has to do that work. In Aurora, that doesn't happen. They all see the same storage. And while the writer does send its change stream to the readers, that's strictly just to inform the reader of, the new state of the database. The reader doesn't actually have to apply those changes. It just keeps its buffer pool, its page cache, up to date using that stream. And if a change isn't in its page cache, it simply ignores that and doesn't do any more processing with that data. So Aurora does more with less. And what that also means is we can optimize for higher throughput, for higher concurrency. There's less I/O, there's less network traffic going across that cluster between the reader and the writer nodes. So we can have that node do a little bit more, every one of those nodes. So you have higher concurrency rates, you have higher levels of throughput compared to a traditional kind of MySQL or Postgres environment. An individual query, when you take it in isolation, may be faster in Aurora than in a comparable environment, but you can all run usually more of those concurrently in Aurora than in a traditional environment. That's what we mean by optimizing for high throughput. So from an architectural perspective, when I look at the foundational architectures that customers start with whenever they're adopting Aurora, there's really 2 foundational architectures. In a cluster with multiple nodes in it, you either treat all of your readers the same and you load balance across all of them, right? They're not distinguishable, so to speak. Each one of them can handle all the load for your application, or you don't. So let's see what happens if you do treat them the same. Usually, in that type of a cluster, all those reader nodes have the same size as the master, because any of those reader nodes can be a failover target, right? And the application uses the cluster endpoints. The cluster endpoint itself always points to the writer node. Even if there's a failover, it will follow that writer. And then the application also uses the reader endpoint, which is a cluster level endpoint that does round robin across all of your readers. And then you can use auto scaling to add and remove reader nodes based on demand if your application needs that level of read scaling. And one tip that we can offer to customers that use this architecture is you do want to monitor the topology of your cluster for faster failovers. Traditionally, database drivers for MySQL aren't really cluster aware, right? There's really only one today that actually has cluster awareness. It's the MariaDB connector for J. And if you don't use that platform, obviously you would want to implement some intelligence into the application layer. And we'll talk a little bit more about connection management and making failovers as quick and as unobtrusive as possible later in the talk. And of course, the other architecture is if you treat your readers differently. They all serve different and very specific purposes. So for example, you might have a cluster with a master node, and you have a read replica that's the same size as the master, sits in a different availability zone, and is dedicated as a failover target. It's just there in case the master has any sort of disruption or issues. But you might have also a whole bunch of other readers there that serve different workloads, a reporting server, for example. And for this architecture, the failover tiers matter because that's how you inform to the cluster that you have a desire of as far as which node should be the preferred failover target and which node is less preferred failover target. You can never exclude a node and set it aside that it can never be a failover target, but you can establish an order of preference. And in this case, applications would use custom cluster endpoints, right? It's a feature that has been launched about a month ago that allows you to essentially build custom endpoints that target different nodes in your cluster. And you can use that to control which applications interact with which ones of the nodes. There's also a little bit of a caveat to this architecture. Because this is a shared storage cluster, all of the data structures, including the undo log, is shared between all the nodes. So that means that if you are in a position where you have workloads that have very, unoptimized, long-running queries, ad hoc queries, bad queries in general, even if you run them on the reader, it might still impact the performance of your writer or other elements in the cluster. So that's important to know. Because you want to make sure that those types of workloads don't impact your other nodes and your other workloads running on the same cluster. So now that we understand kind of how the architecture works and what's our starting point, right? Of course, on these architectures, you can build on top of it. You can add cross-region read replicas. You can expand them with the types of features that we launched this morning, the global tables where you have physical replicas in other regions. So you can build on top of this architecture to scale it to the needs of the application and other types of kind of requirements that you may have from a compliance point of view, for example. But what about automation and deployment? Now, a lot of you are using automation today for various parts of their applications. Typically, we rarely encounter customers that go into the console endpoint and click manually spin up production clusters, right? And the reason for that is relatively simple. You want to reduce the risk of human errors. You want to ensure that you have repeatability, especially if you want to provision many pre-production environments that are all consistent with what production looks like. And there's auditability, accountability, and change management that comes into play there as well. You always know what changes are made because they're captured somewhere, right? Either in the form of a script or in the form of a template that evolves over time, right? But the two ways that you can accomplish that generally with any sort of workload is either you do all declarative automation with CloudFormation or Terraform or tools like that, where you specify how your infrastructure is supposed to look like at the end, including the database in this case. What's the cluster look like? How many readers, endpoints, and so forth, and so on and so forth. Or it's procedural. You have a set of scripts that you invoke the APIs, do this, do that, you know, bring it from state A to state B. But Amazon Aurora clusters are stateful resources. You know, it's a cluster. You store data in it. Over time, you know, that state changes. And the big question here is to what extent those tools that you're using reflect that and track that state. So let's look, for example, at declarative automation, things like CloudFormation, for example. You would build a template, and you tell the tool how that infrastructure is supposed to look like at the end, right? And the tool then goes in and provisions the resources in the right order based on its optimizations and its logic, the most optimal way of getting you there. And then 6 months later, you need to make a change. You update your template, you let CloudFormation or Terraform, whatever the tool is, go and, you know, make those changes, right? Now, the question there is, does CloudFormation or that tool reflect the state or data changes that you've made over that period of time to your cluster? And the answer is no, most of the time, right? So if you're in a production environment and you want to minimize downtime with any sort of change that you're making to the database, you got to ensure that the tool that you're using can actually handle that or actually factors that those types of decisions in. It may or it may not, and if it's not, then you need to build procedures and runbooks and other alternative ways of tracking that outside of it. The common question is, for example, you know, how do you do a point-in-time restore, for example, right? If your Aurora cluster is managed by CloudFormation and somebody accidentally deleted a table 1 year after you've launched it, how do you do a point-in-time restore and do that using CloudFormation? In many cases, you can't seamlessly do that, right? It would be an external action that you would have to perform outside of CloudFormation. With procedural, you have, again, a different set of concerns. It's not that necessarily one is better than the other, but with procedural automation, you got to think about the steps that I'm defining and make sure that you're validating that the initial state meets those expectations, because then you face otherwise you face a garbage in, garbage out type problem. If you apply the set of transformations and steps to your infrastructure to get you from point A to B, and it turns out that your cluster is not in a state that's an expected state from a point A perspective, you might also not get necessarily to B. So there's different kind of considerations, but typically tools like CloudFormation and Terraform are very, very popular as far as deploying and managing Aurora clusters. So whenever you're using something like CloudFormation, there's a couple of things you got to think about. Check the feature gaps. See if there's any gaps between what CloudFormation can support versus what the APIs can support. Very recently, we made a lot of improvements to that, so you can do all of the cool new features that are available now in Aurora. You can support them using CloudFormation as well, natively. There might still be some gaps, and at different times as we're launching new features, you might find that CloudFormation may trail a little bit behind. And at that point, if those gaps are relevant to you, are there any ways you can work around them using CloudFormation? Custom resources, for example, where you have, for example, a Lambda function invoke the APIs to bridge that gap. Does that make sense? In some cases it does, and it works very well. But there's also aspects and considerations around ordering. In what order do I execute the steps, right? For example, right now, if you want to assign a role, what you need if you want to invoke Lambda functions or interact with S3 for import-export from an Aurora cluster, that is still not natively supported in CloudFormation. So you would use a custom resource, but you have to invoke that custom resource before you provision the nodes of your cluster in CloudFormation, because otherwise it's going to take much longer, right? If you do it after that, then the cluster change is happening, and then that cluster change invokes a reconfiguration of your nodes and that will take a little bit longer. So timing is also important, and ordering is important. And of course, if you need minimal downtime production workflows, right? If you want to do a point-in-time restore and update, if you want to upgrade, for example, Aurora from 5.6 and go to 5.7, right, on the MySQL side, you can't do that directly and natively in CloudFormation without a more extended downtime, right? If you want to do minimal downtime in that type of a scenario, you would have to make some changes in CloudFormation, like provisioning a new cluster 5.7 out of a snapshot from the old one, change your template to have that new cluster, but then you also want to do bin log replication, which is an action outside of CloudFormation, and you have to worry about things like, how do I catch this, and how do I record these external actions in a way that later somebody can audit and see that those actions occurred, right, from an auditability point of view, and what automation and other scripting I can use to supplement CloudFormation with, for example, in that use case. So there's many different considerations of this type that come into play. So now that we understand a little bit how the architecture side and automation side works, let's look at some of these features that are helping you be more agile from a dev and test perspective. And the reasons for that are because we've actually seen a lot of antipatterns, in our jobs working with customers like you. And this isn't something that necessarily affects one or the other, but every one of us has experience at some point working with an application where the testing was done on very tiny subsets, not relevant for production scale. You didn't have the ability to simulate the scale of production and test environment. So this is an anti-pattern because whenever you're tuning your performance or your queries, what you expect in development and testing may not be reflective of the production scale. Bulk exports of data from live production systems is also a pain point because they are disruptive, right? If you're downloading a lot of data from your production database, it will impact performance of that production database, which is limiting in multiple ways. It's limited as far as when you can do those extracts, which limits how fast and how many times you can actually do them, and it's limiting in other ways as well. Unoptimized queries on cluster readers running them, I think we've seen probably the longest query that we've seen running by a customer on a reader was 29 days. I mean, if you're in a position that you're running on a relational database, a query that lasts for 29 days, that's problematic architecturally, but it was also impacting the performance of that entire cluster because a read view was taken that was held open for that entire 29 days, and the size of the undo log to ensure that other read views, to ensure that the data was accurate as far as that transactionally accurate for that particular long-running transaction, the amount of undo logs was starting to slow down your writer node because it was blocking the purge threads, it was blocking a garbage collection, and so on. So the entire cluster was starting to slow down. I mean, there's not necessarily a number threshold where things get slow, but there are some limits and reason that should be applied within reason. So the right way, of course, of doing some of these development and testing experimental work is knowing the types of features that are available in Aurora. Point-in-time restore is one that helps, restoring from backups or corrupted data or things like that. Database cloning and backtrack are other two big features that will help development and testing be a lot more agile. And they will also offer workload isolation where you can isolate some of these development concerns from your production system. So database cloning, it's a way for you to get access to faster access to copies of your production database, for example. So you can test changes in a pre-production environment and see what the impact might be, and also leverage a relevant sized data set. You can also use cloning to reorganize your database, if you need to add an index and you have a very, very large table, you might not be able to do that realistically in production because it might be way too disruptive. So you could create a clone, add that index on the clone, catch up using bin logs, and then simply cut over. Makes things a lot simpler, and it decouples that operation from your production workload. And then another cool real workload that we see clones used for is folks that need to do analytical. I need to run reporting and build some dashboards and analytics every hour or every half an hour or every day, whatever that time frame is. Those are heavy queries that maybe in production would be disruptive. So you would spin up a clone, run those queries, dispose of the clone, and then an hour later or a day later when you need to do the same thing again, rinse and repeat. And you can automate that really, really well. So cloning is available for both MySQL and Postgres compatible versions of Aurora. And really the cloning takes just a matter of minutes because we don't actually copy the data. And the data copy operation really only happens if you make a change on the clone. And the cool thing about that, of course, is that you're also not paying for that additional storage, right? It's only for the changes the data changes that you make on the clone. That's the only thing that you would be having an additional cost for. And the operations are isolated to the extent that the source, the master, doesn't actually get impacted by your whatever is happening on that clone. And you can have up to 15 clones inherited essentially from the same source volume. And another feature that's a little bit complementary to this and helps agility in terms of development and testing a lot is backtracking. And backtrack is a way for you to move the database back in time, move the state of that database back in time without having to go through a costly backup restore type operation. So that's used to generally reduce the risk of any sort of database changes at scale. You try, if it fails, you backtrack, right? It also helps you mitigate, things like unintentional DML, DDL changes, or if you have a malicious actor that suddenly kind of manipulated your data in the database, you can easily replay that back. And again, it avoids those time-consuming backup and restore or point-in-time restore operations. So I mentioned that our storage is log structured and distributed, and the unit of segmentation there is what we call a segment or a protection group. That is a logically 10 gigabyte chunk of your data, and your storage volume might be terabytes in size, and it's comprised of many, many of these 10 gigabyte chunks. So for all of these 10 gigabyte chunks, every so often we take a snapshot. We materialize all the changes up to that point, take a snapshot. And then from a backtrack perspective, any change to your data that happens after that gets kept as a change record, which is a delta. It's just a change vector. So when you do want to do a backtrack operation, all we would need is essentially a point in time, and we figure out what is the most relevant snapshot, then apply all of those change records. We do that all in parallel across all of those segments, so it's really, really fast. And, then we present you with a new database state. The most important thing about Backtrack is that it's not destructive. We don't actually change the data. You can go back in time, and if that time point is not relevant, you can go back a little bit in the future. I mean, in the future from that point of view, but, still up to, the present day. But you can find that right time of where you need to restore your database. And Backtrack is available for a desired period of up to 72 hours. So you can backtrack as far back as 72 hours. And you pay for the volume of those change records that we retain during that time. So, in most cases, that cost is really nominal for leveraging this type of a feature. And of course, you know, right now, Backtrack is available for Aurora MySQL 5.6. We're, of course, working to bring that to the other Aurora engines and versions as well. And I want to show you a demo of Backtrack in action. So here's how this works. I have here a database cluster. This is in the RDS console. We're looking at a sample cluster. This is a highly available cluster, so I can click on the instances panel, which, by the way, the console just got updated and changed today. Unfortunately, we couldn't record a video. You can see which nodes in my cluster are the reader and writer. This is highly available across 2 different availability zones. So I can log in to this cluster using my MySQL command line. And on this cluster, I have a simple HR, an employee database, right? So it's a simple system. It's a simple sample data set. And what I'm going to do, I'm going to add myself as an employee to this fictitious company. You can see that we have different tables with salaries, employees, titles, departments, and so on. So I'm adding myself as an employee to this company. And I'm going to give myself a salary. And I've been a little bit too optimistic, and I actually put one more 0 there. You can barely see it, but it's, you know, I have a little bit too big of a salary, so I'm going to fix that. And I'm going to update that record to fix my salary. But I've made a mistake here. I forgot to put the where clause, the predicate clause, and I'm actually resetting everybody's salaries in this example. Oops, that's bad, clearly. If this would be production, I would be panicking right now. So what do we do? How do we fix this? Okay, so I'm going to exit out of the database. I did enough damage here. And I'm going to go ahead and backtrack. And I have a timestamp here. I used actually a couple of current timestamp queries there to kind of find, you know, for demo purposes, the right time spots. So I'm going to backtrack to this point in time. I'm getting the information from the system. AWS will tell me that the request has been scheduled. It's pending. I can switch back now to the console and track the operation. It takes about 2 minutes normally. We fast forwarded a little bit here. You can see the state changing there in that green box. You can see that the nodes are reflecting the fact that the cluster is being backtracked. And this is an operation, so when you make this operation, then all the database connection will be interrupted, right? This cluster will be restarted, so there will be a little bit of a disruption. Okay, my cluster is back online. My database is available again, so I can log back in. I'm entering the password, and let's see what happened. Again, I'm using the employees database, and I'm going to check if my employee record is still in the database. And it's not, so clearly I went a little bit too far in time with this one. So I'm going to backtrack again. I'm going to exit out of the command line prompt, switch over, try to backtrack again, now to a different point in time that's slightly in the future relative to the last time I've actually backtracked. And we're going to go through this again. Again, the cluster is in a backtracking state. This normally would take about 2 to 3 minutes. I'm going to refresh here the interface to make sure, and everything is back available right now. And I log in back into my SQL console, and let's see what has happened. Okay, my employee record is there, right? So I've moved a little to the right spot. Now let's see what happens with the salaries. And the salaries are all fixed again. They're all different values, so that's good. So I basically fixed a very potentially costly mistakes in a matter of a few minutes by just simply replaying back the database to the state. Now, key to understand here, Backtrack works at the cluster level, so you wouldn't be able to just replay back one table or another table. It's the whole database or nothing. All right.
All right. Thanks, Vlad.
Absolutely.
All right, everybody. So we're going to jump from here into availability and performance-focused database development. So, again, looking at sort of the best practices versus anti-patterns that we've seen, out there in the wild, so to speak, is, this app development testing on tiny subsets of production data, considering that, my database is always there for me and never fails me. I mean, that's something that's not always necessarily true in a lot of cases, right? They're running the long, unoptimized queries on cluster readers, like the example that Vlad gave of the 29-day query. Right? And then lack of outcome focus, right? Not really having a clear direction on what you're trying to do. It's important to start with the end in mind so that you have something that you know that you're working toward. So the right way is, to be aware of the architectural differences between Aurora and equivalent engines. Vlad's touched on the log-based storage system that Aurora has, which is fundamentally different than most other engines that are available on the market today. And so that gives us features like Backtrack and cloning that are otherwise just not available, or maybe cost prohibitive if there's something that's similar or comparable, right? So that's something that you have now in your tool belt that you can consider as you are doing your development and managing your databases. You want to be able to know about the Aurora capabilities and operational procedures, the automated failovers and upgrades, how that all works, sort of understanding, what it looks like during a failover and, how best to architect for that, right? And then, extending Aurora features with application-side cluster awareness. Again, understanding that, you have a single writer and then 0 or up to 15 readers, and then understanding during that failover process which one is which and how to determine what those are, and to use tools, if possible, that are aware of those differences. And again, test, don't hope for the best. There are procedures within Aurora. Aurora was built with failure injection queries available, where you can simulate things like the loss of a disk, like a failover, other things like that. It's something that, failures happen in the real world, right? And so, Werner Vogels is known for saying everything fails all of the time, right? So it's not a question of whether something fails, it's how are we going to be prepared to deal with it when it does happen, right? And so that's something that, Aurora has been designed to be very robust, self-healing, and can address a lot of those things, but you still need to be aware of that from an application perspective. So with regard to connection management and availability, most common MySQL and Postgres drivers are not cluster or topology aware. When we created Aurora, it was important that we made it what we call wire compatible. And so what that means is that if you take an application that's using, for example, MySQL 5.6, and then you point it to an Aurora MySQL 5.6 cluster with the same data, your application won't know the difference. Right? And so what that means too is that your drivers will still work. But of course, when the original MySQL drivers were created, there was no such thing as Aurora, and so there was no functionality built into those. So the Maria driver that Vlad talked about earlier is an example of a topology-aware driver that you can use. Client-side connection pooling, recycling connections periodically and avoiding connection storms. One thing that's nice about Aurora is that it is designed to handle, many more connections than your average, say MySQL cluster. The current limit is 16,000. You can easily handle 5,000 connections without skipping a beat on an Aurora cluster. But you still want to make sure that we're leveraging connection pooling so that we don't have to go through that costly operation, the handshake that has to take place in order to establish a connection into any database instance. I mean, it's not even Aurora specific, it's any database instance, right? Using a smart driver like the MariaDB driver, for example, or build topology awareness in your client data layer and validating connections. Something that I see sometimes with customers is during a failover event, what they'll do if their application is not aware is that there will be a failover. And what happens during a failover is that the writer becomes one of the readers, and then one of the readers becomes a writer. And so what you might see is getting errors back in the application saying, this is a read-only instance, you can't perform write-based queries here. And that's because what's happened is the application has not picked up on the fact that those two have switched places. Now, failover with Aurora is based primarily on DNS, right? So within Aurora, there are different endpoints. There's a cluster endpoint, which always follows the writer. And you should, as a matter of course, point your application to that endpoint for all of your read-write applications. If you are able to split the load into a read load and then a write load, then the read-only load could be sent to that reader endpoint that will do a DNS round robin across your pool of readers. Now, what we're using here is we're using DNS aliases, CNAMEs, right? And the time to live, the TTL on these records is currently at about 5 seconds. So under normal circumstances, if your application is aware and if it respects that DNS TTL, then during a failover, in about 5 seconds, your application will requery DNS to realize what the new endpoint is. If your application is not doing that reliably, that's when you might run into trouble like I was describing with, getting the error saying that there was a write attempted on a read-only instance. And that also covers point number 4, which is the behavior of Aurora DNS endpoints and managing that DNS caching. So now the next thing to consider is monitoring the performance of your queries. And earlier we had some points where we were talking about, essentially start with the outcome in mind, right? And I work with a lot of customers that will say, well, my CPU is high on this instance, so that means that I must be having performance issues. And I would say not necessarily, right? The purpose of the database in the application is to store, modify, and retrieve data, right? And so what we want to do is not measure how much CPU it takes to do that, but how effectively we're doing that. And so the metrics that I generally recommend to look at are query throughput and query latency. Those two numbers will give you the answers to how many queries am I processing per second, and on average, how long does it take for me to process those queries, right? Now those numbers will vary from application to application, so what we would recommend is that for your application, that you run a representative workload and then gather those metrics from CloudWatch, is where you would find those CloudWatch metrics, and then say, this is my baseline. These are the numbers that I know are what I am going to expect from my application when my application is performing correctly. Now, if those numbers get out of whack, then you might take a look at some secondary metrics like CPU. Maybe they are out of whack and maybe the CPU is to blame. And then you can start to look into that. But start with that baseline first. Then you want to assess the performance of different workload impacts, right? So maybe you've introduced a new index to your database, or maybe you have a holiday sale that has driven a lot more activity to your database. And so then you come back to your baselines and compare against those baselines. If you find that there is an issue, troubleshoot using these tools that we're about to talk about in a second. And then the last thing that I want to touch on is effective capacity planning, right? So a lot of things within Aurora can be, automated for capacity planning. For example, if you're able to split your read and write workload, it is possible to auto-scale the readers that you have in your cluster, where you can automatically, based on load, increase and decrease the number of readers that you have in your pool. But you also need to consider about whether you're going to even be able to use readers if your application is such that it can leverage that. Or when we're looking at write workloads, what size instance am I on and how am I going to scale that up or scale that down should the need arise. Now the tools that come with Aurora out of the box are Amazon CloudWatch metrics, which is where you would look for things like that query throughput, that query latency. You would also get some of the secondary metrics like CPU utilization, buffer cache hit ratio, for example. And then we have CloudWatch logs, which is where you could, if you so configured it, send things like your slow query log, Or if you've enabled auditing, you can send your auditing logs into CloudWatch Logs. And then once they hit CloudWatch Logs, you can either use third-party tools to analyze those logs and respond to them, or you could do it manually, or you could leverage something like Lambda that can analyze those logs as they're being generated and maybe even take a prescriptive step that you've already pre-decided, right? Enhanced monitoring gives you insight into over 50 different operating system level metrics. And then the last one that we have listed on here, Performance Insights, was released a few months ago, and that allows you to have query and weight level performance data. And as we look at this, you'll notice that it kind of goes from left to right, where the broader is to the left, and then we get into some of the narrower as we get to the right. I mean, on the left, if we've determined that we have a performance issue and we need to drill into it, then we can get down all the way into the query level itself with Performance Insights. So now Performance Insights itself is available on both the MySQL and the Postgres-compatible editions of Aurora. It's got an easy and powerful dashboard that you can see a screenshot of right there on the right-hand side. And it helps you to identify not only the source of bottlenecks, but also the top SQL queries that are consuming resources and weight statistics too that are contributing perhaps to performance issues. You can adjust the time frame. By default, we show you an hour window, but you can expand that out. You can either bring it in, say 5 minutes, out to 24 hours. And you can also select a given segment and zoom in on it. By default, we offer 7 days free storage of these performance metrics. That's usually adequate for most performance tuning purposes. But if you are interested in keeping that data around for a longer period of time, you can pay a nominal fee to keep it around for up to 2 years. There's also API access into Performance Insights so that it will integrate with other third-party tools if that's something that you're interested in. So I'd like to give a little demo here of what Performance Insights looks like in action. And so right here, what we're looking at is we have a cluster. We're looking through the RDS console, and that cluster is comprised of 2 different instances named Demo Node 1 and Node 2. And remember, the names might be misleading. You might think that one is a reader, one's a writer, but the only way for us to really know is to look over here to the right, where we're going to look at the replication role. And now we know that the top one is the writer and the second one happens to be the reader. But that could change at any time, again, in the event of a failover, etc. So what I'm going to do now is I'm going to log in, and I'm going to use a TPCC-like benchmark from Percona that's going to create a schema, and then it's going to use 16 threads to populate that schema and run read-write queries against that database, right? And we're doing this really just for the purpose of generating load. Now, if we go back into the console and we zoom in on that node, we can look at the CPU utilization, and you can also notice on the right that the DB connections count is at about 16. And remember, we use 16 threads, so that's about what we would expect it to be. And we can see that the CPU is ramping, and so are the DB connections, but you can see it's just started, right? And so, after a minute or so, the traffic is flowing through. And so let's go over to the Performance Insights console and take a look at what's going on over there. So here you can see we have the 2 nodes that we currently have Performance Insights enabled for. We select the first one where we're doing our read-write workload. And so we don't have any data showing up in there, but if we give it just a second and refresh, you can see we now have some data that's streaming in. This is the main console where you can look and see what type of activity is happening in that database cluster. You can see across the top where you specify the time period and then the weights that are listed along the right-hand side, which correspond to the graph that you see. You might also notice that black line across the top right under the vCPU. What that represents is active sessions. An active session would be, it's how many sessions for a minute. So for example, if you had one query that ran for 1 minute, that would be 1 active session. If you had 60 queries that all ran for 1 second apiece, that would also comprise 1 active session. And so that line gives you an idea of the threshold for that particular instance as to what it can handle. In this case, we're still under that line, and so our performance is still within the realm of what this particular instance can comfortably handle. All the same, you can see as time goes on, it's starting to move across the screen, and we're getting more data. So if we scroll down, we'll notice that this is a list of all the queries that are being executed against that instance. And you can see that the commit statement is the one that is generating far and away the most weights. And if you look at that, you can see that the color is that brown-orange color, which aligns with, I/O, right? I/O type of weight that's happening there. Now, you can see underneath, we have all these other update, insert, etc. queries. And the top is sort of a hash. You notice the ID is a question mark. When we expand it, you can see that there are actual queries with the actual parameter that has been specified. So this allows you to drill in and see what are the queries that are actually causing the load. You could then, of course, take those queries and run an explain against them to find out more about what it is about the query itself, right? So now we've been running this for a little while, right? And we've been running this with 16 threads to see what that looks like. Let's go back and let's rerun the same test, but this time we're going to do it with 32 threads. And let's see what kind of an impact this has. So again, we'll refresh it. We'll wait for a little bit for some of that traffic to generate. And then as that's coming through, you can see that it is significantly more, as we would have expected, but now we've actually exceeded that dashed line across there. So that's indicative to us that we are exceeding what we would otherwise normally anticipate is an appropriate load for that particular instance. And again, you can see the weights along the right-hand side. You can see there is some CPU in there, that's the green, but then you can see that sort of orangish brown that we saw, correlated with that commit earlier. You can see what that's tied to the IO Aurora redo log flush, which would make sense because we're doing a lot of DML type work here. You can see that I just selected that particular area and it allowed me to zoom in to exactly that segment so that I can focus in on what it is that we're really focused on right now and select that time period. All right? So, what about cost-effective development and testing, right? So we want to be able to use database resources in appropriate scale and only when they're needed, right? So dev and test activities, realistically, a lot of developers, they work Monday to Friday, 9 to 5, right? So we have from 5 p.m. till 9 a.m. the next morning, and then most weekends where maybe nobody's even using that database cluster. And under normal circumstances, that might just be on and running and accumulating a bill for that period of time. The scale of dev and test activities varies. Sometimes you're running full production load. Sometimes you're just running some queries, just writing code. You're not really fully testing load. You're just developing the actual queries that you're going to run in your application, right? And then you also want to have your dev and test environment isolated from production. You obviously don't want to, be the most interesting man in the world and, when I test in production, right? You want to make sure that you're running in an isolated environment. So there are two features that come to mind when we're thinking about cost optimization with Aurora. One is the ability for Aurora to start and stop an instance. So if you're using what we call provisioned Aurora, that would be a cluster where you have an instance, sort of the standard Aurora, the initial Aurora, you can stop the instance and not pay for compute for a period of time. Now, if you stop an instance and you leave it stopped for 7 days, it will automatically restart, but you could stop it manually using an API. So you're then not paying for compute, you're not paying for IOPS, obviously, because you're not running queries, and you're only paying for the storage, which is the least expensive component of the entire equation. The other side is Amazon Aurora serverless. And with serverless, it's the same exact Aurora that we've been using this whole time with the ability to automatically provision and scale up and scale down. And so we find that it's very, very useful for development type workloads, as well as a few other workloads that might be interesting as well. So some of the use cases, like I said, development and test databases. They can be easily provisioned. There's cost savings when the database is not in use because we can scale to 0. Or if you don't want to scale to 0, at least scale to a very small instance type. And you can simplify dev and test pipelines with the knowledge that the code that you write is running against a regular Aurora cluster. It's not a special type of Aurora. It is the same exact Aurora. So if it runs in serverless in a certain way, then you can generally anticipate that it will run that way in a provisioned cluster as well. It's great for infrequently used applications like a low-volume blog site, for example, or the dev test workloads we're talking about, or applications with variable loads, peaks of activity that are hard to predict, for example. The architecture itself is something like this. You remember I said that it's the same exact Aurora that we've been using. The main difference is that we have essentially a managed proxy layer that sits in between the application and the database. And so it's a MySQL compatible endpoint, so you don't need to change your drivers, you don't need to do anything other than just connect with the same tools that you already use to connect to Aurora. And then we have a fleet of routers that manage the queue, client connections, and route the database traffic to the appropriate instance. The instance handles all the database operations, and that's the point where it's just the regular standard Aurora that we've all been using for this time. The data is still kept durable in the highly available Aurora storage volume, just like provisioned Aurora. And when scaling thresholds are reached, we will automatically scale the instance up or down, pulling from a warm pool of instances, right? The scaling operations are transparent to the application. We don't break that TCP connection between your application and the database. Instead, what we do is we look for what we call a scaling point, and that is a brief moment in time between your transactions where we can pause your connections and then unplug the original instance and then plug in the new instance and then resume. That operation, on average, takes somewhere around 5 seconds. So it's not a break in your application. It would just look like an additional 5 seconds or so that your queries took, that it took to run those queries. You can configure the minimum and maximum capacity and whether to scale all the way down to 0 if there's no activity. For example, your developers go home at 5 o'clock and you specify if there are no queries within 1 hour, spin it to 0. The next day, your developers come in. The first person that connects to it will need to wait around 20 seconds or so for it to spin back up, but then it's business as usual. So there are no API calls necessary, and it just happens for you automatically. Serverless pricing is a little bit different. If you have a steady state database workload, you're likely going to want to use provisioned Aurora. But if you have these spiky workloads, you would want to take advantage of the serverless pricing. On the right-hand side, you can see some examples of particular real-life instances. But the important thing to note here is that the capacity is measured in Aurora capacity units, or ACUs. It's very similar conceptually to how we handle Lambda functions, where one ACU is equal to about 2 gigabytes of memory with the corresponding CPU and network capacity. There's a flat rate per second of ACU usage with a minimum of 5 minutes of usage each time the database is activated, right? And then the storage and I/O are billed the same as provisioned Aurora. One other thing that I wanted to bring up is that we recently introduced the RDS Data API. And what this is a public HTTP API endpoint that's integrated with AWS authentication. It's automated server-side connection pooling. So if you have applications that need to take advantage of connection pooling, some of them are not capable of doing that. This is something that does enable that connection pooling. And it's ideal for Lambda and serverless applications, right? Where you can connect via HTTP rather than trying to maintain, say, a connection pool inside of a Lambda function, which may otherwise be transient, right? It's fully integrated with AWS Secrets Manager and AWS AppSync. And then there's an optional session construct for efficient prepared statement executions. We also, as part of this, released an interactive query editor in the console so that you can run ad hoc queries through the console into your serverless cluster. And that's the last point that I want to make, which is today, as of the initial, and it's in a beta phase right now, but as it stands today, it's only available for Aurora serverless on MySQL. but that is, something that, we iterate on this. And so as this grows, I think that it's a very exciting opportunity. So some of the parting thoughts that we have that we just want to kind of recap with you is that, as Vlad was pointing out, you want to use automation wisely and map out your operational processes in detail so that you can make intelligent choices between using, the more the described, like CloudFormation, Terraform versus procedural deployments. You want to know Aurora's features, how they can improve on your development and testing processes, develop and test with performance in mind, and then quantify your expected baseline performance of your workload so that you know what you're working toward. We want to thank you for coming out today. We want to share with you that there is a companion workshop. 2 iterations of it are already complete. There is a 3rd one tomorrow. It's very similar to what we've talked about today, but it's more of a hands-on workshop. So the things that we covered, you can do hands-on. And then we also have a couple of related breakout sessions if you're interested in learning more about Aurora. And then we also want to remind you to please complete the session survey in the mobile app. And so we want to thank you again for coming to reInvent and specifically for coming to our session today. Thank you, everyone.
Yep.